Nachiketh here, and this is not Vsauce, but we'll be going over gravitation and Kepler's laws. This is one of the interesting topics that we'll be learning this year, and this is one of my personal favorites. So, diving in, we're going to go into force of gravity. So, basically, when there are two objects, they exert the same force on each other. The magnitude is the same, but it's in the opposite direction. So, let me show you. There's A and there's B. Let's label them. So, A would have a force of E long, and B would have the same exact vector, the same size, same distance, but it would be in opposite direction. So basically, you're applying the same force on Earth as the Earth is applying force on you. So you're pulling the Earth towards you as the Earth is pulling towards it. And this is the equation you really need to remember to find the force of gravity. 99.9% you're going to have this with you during the test, but if you're taking notes, I take that down. So, let's dissect this equation. My apologies for that. So, big G right there. That's a gravitational constant. This number, you won't have to remember it, but this is basically what it is. This is the number that ties in this whole equation together. And M1 is the mass of object 1, which in most cases would be the mass of Earth. And M2 is the mass of the satellite or whatever you want to find. And the R is the distance between them. So, going to the next slide. Gravity on Earth. So, I'm hoping most of you know that the acceleration of gravity on Earth is 9.8 meters per second squared. You might be using it in your previous problems and other chapters, but here we'll try to find out why it's 9.8 meters per second. So to do that, we use F net equals ma, and for the F net, we use the force of gravity equation, and then ma. So this would be the mass of u, and this would be the mass of u. So that would just cancel out. That's why it doesn't matter what your mass is, but everyone's acceleration is the same exact thing, no matter what your mass is. So here you have big G, mass of the Earth. This also would be given to you. You don't have to remember it. And the radius of the Earth. And when you crunch all that numbers in, type it in your calculator. Well, hide it. Wait for you to solve it. And ta-da! You get 9.81 meters per second. If you did not get that, I would redo the calculation. Okay, so going on. Gravity on Earth. So basically, since there's a r squared function right here, 1 over r squared, so it's inverse r squared. So this is the proportion it goes to. So the force would decrease the further you go away. Asymptotically, it goes to 0. So when you're infinitely far away from Earth, then only can you get away from Earth. So, sorry guys, there's no escaping Earth's gravity. Alright, let's do a quick practice problem. Erase the board right here. So, we need to find Fg equals big G times mass of the Earth times, so 1,500 kilograms all over. And remember, this is going to make sure this doesn't trick you. It's in kilometers, so you have to convert it into meters. So 120 times 1,000 squared. Right there. And We'll crunch that into our calculator. So first we need to find the big G. So 6.67 times 10 to the power of negative 11 times the mass of Earth, 5.97 times 10 to the power of 24 times 1500 kilograms. And then in the bottom we have 120 kilometers times 1000. Square that number. Boom. That's the force. But you also have to take into the account of the radius of the Earth. So we'll not go over that. You have to add in that in your when you're getting the radius. But this is basically a wrap-up course. Trying to get used to this, so we're on a time crunch. Okay, so next topic, gravitational energy. There we go. Sorry, I was looking for my marker. Gravitational energy. It's also very similar to the other equation, force of gravity, except if you notice here, there's no r squared, it's just r. So if you remember that one thing, you're perfect for the test. Alright, next thing, Kepler's law on planetary motion. So the first thing Kepler says is planets move in elliptical orbits around the sun, and the sun is one of the focus. So basically, if this is the sun, the planets move in an elliptical orbit. So that's one of the focus, and excuse my drawing, but that would be another focus. So the sun's like at one of the focus, and the planet's like happy little planet. Okay, so the next thing Kepler says is if you track like the distance around like the path it takes, and if you time it, so it would take the same amount of time for this to go like, so it goes around like quicker, closer to the star, and goes slower further away. So the areas are always the same. So this is not drawn to scale, obviously, but this would be really long and this would be really short, but like wider. So the area is always the same. And I believe that's the end of our video, and thank you for watching, and just remember, this video is sponsored by Energy Balls, #surface area.